I want to thank the organizers for inviting me to be here today. It's quite an honor. I also want to acknowledge that a lot of the story that I get to tell you today comes from a research group at Georgia Tech that I get to work with very creative undergraduate, graduate, and postdoctoral scholars. So with that, the main goal of my talk today is really to highlight how we can transition chemical fertilizer manufacturing from something that looks like this to something that looks like this. It may seem like a far stretch to imagine that we can transform something that is made at such large scales to the farm scale, but the work that we've done in my research group over the last 5 years gives me confidence in saying that we can. In order to attain this goal, there's going to be a lot of advances that we need in terms of separations and catalysis to make this process green. And I hope to highlight some of those in this talk today. But before I go into the details of the science and the engineering, I want to take you back a little bit. Maybe you remember this nursery rhyme growing up. It's called Oats, Peas, Beans, and Barley Grow. I remember learning it, and I grew up in Philadelphia, Pennsylvania, which is not known as an agricultural center. But if you don't remember it, I'll refresh your memory. There's a common refrain in this nursery rhyme which repeats itself. It is, oats, peas, beans, and barley grow. Do you or I or anyone know how oats, peas, beans, and barley grow? The nursery rhyme goes on to have many different verses that actually discusses how oats, peas, beans, and barley grow. It talks about how a farmer needs to plant seeds. They need to irrigate seeds. They need to weed around the plant as it grows, and then they need to harvest the plant. And then they need to harvest the seeds that fell. It's a very famous nursery rhyme, and it does a really good job of educating children on how food is made today. What's interesting about this is that in no place during this nursery rhyme does it mention applying synthetic fertilizers. But if you look carefully at the nursery rhyme, it does talk about how nutrition is maintained in the soil. The choice of oats, peas, beans, and barley is not random. When this nursery rhyme was written in the 1600s, crop rotation was the main means of replenishing the soil nutrition from season to season. While oats and barley were planted in the fall, uptaking a lot of the nitrogen nutrients in soil, peas and beans were placed in the springtime to replenish the nitrogen nutrients in the soil. The farmers also knew that if they allowed the crop to decompose, that nutrients could remineralize the soil so that they could have consistent agricultural crops season to season. If you fast forward to today, we still largely use crop rotation and cover crops to maintain soil health. But in order to maintain agricultural yield, we have transitioned to synthetic fertilizers. Synthetic fertilizers are typically ammonia-based. They come in urea, ammonium nitrate, and hydrous ammonia. Typically, you'll buy them as a solid, and they typically will have 30 to 80% nitrogen. That's good because we want to supply nitrogen to increase our agricultural yield, but that's bad because plants are not always ready to uptake that nutrient. And so the reason why we apply 30 to 80% nitrogen is because we make ammonia in such a distributed way in only 100 locations around the world. And so in order to ship these fertilizers, it makes most sense to put as much nitrogen in the compound as possible. So we ship solids rather than liquids because it's easier. We make fertilizers with 80% nitrogen rather than 10% nitrogen because it allows us to make more product and ship it further. So, why did we start using synthetic fertilizers? Around the turn of the 19th century, there was a giant growth in global population, but our land, our arable land, was yielding the same amount of agriculture. And there was a scientist, Sir William Crookes, who basically stood in front of a venue like this and told scientists, As mouths multiply, food sources dwindle. And what he charged scientists to do was to develop a technology that could enable on-demand nutrient production so that we can increase agricultural yield. And it wasn't until things like the COVID vaccine that the rate of development happened so quickly. Within years, two scientists, Fritz Haber and Carl Bosch, had developed the science and engineered the solution to this problem. And that's why we have the Haber-Bosch process today. The Haber-Bosch process is a simple thermocatalytic reactor which has a packed bed of an iron-based catalyst. We separate nitrogen from air, and we produce hydrogen using fossil fuels. And when you supply hydrogen and nitrogen in the right ratios, and they interact with that catalyst at high temperature and high pressure, we can produce ammonia. The keys to the system are that it has to operate at high temperature, 500 degrees Celsius, and it has to operate at high pressures, around 400 atmosphere. This was a very innovative solution and a very good demonstration of an acceleration of science and an acceleration of engineer to meet a global challenge. It's also been a great demonstration of economies at scale. As an engineer, this is what we learn about in our engineering classes on what is good about engineering. If we learn how to scale things up, we can decrease the cost. You can see by this diagram here that with $500,000, you can create a Haber-Bosch plant that can get you a capacity of 10 kilograms of ammonia per day. But the normalized cost will be near $100 million per ton per day. If you scale that up to 1,000 tons per day, your normalized cost can be cut by 10 times. That is tremendous. The challenge is you need $1 billion to build that plant. So with all that, I want to highlight that the Haber-Bosch process has also often been called the most important invention of the 20th century, and it supports today globally half of our global population. This graph on your y-axis is global population, on your x-axis is year. The key to look at in this graph is the pink region. That's the percentage of the global population which exists because of synthetic fertilizers. That region is not declining, it is growing, and so we are heavily dependent on this process, and it's very important. But the downside, we now know we have many other global challenges right now, famine being one of them, but climate change is also significantly increasing at an alarming rate. Ammonia production has the largest greenhouse gases emitted of any chemical commodity. And the volume with which we produce this chemical is very large. So the carbon footprint is not sustainable. It's estimated that 340 metric tons of CO2 per year are emitted to make this one chemical commodity, and nearly 80% of that goes to making synthetic fertilizers. It's also increased inequity in access. You can see the regions on that graph there show where black dots denote where we have Haber-Bosch plants. You can see a lot of Haber-Bosch plants in North America, a lot of Haber-Bosch plants in Europe. You do not see many black dots in Africa. The green dots denote where there are agricultural centroids, where we need to grow food to feed growing populations. Those agricultural centroids are everywhere, and there's many in Africa. And then the color map behind the screen shows you the cost of fertilizer depending on where you are. You can see very yellow and orange regions in North America showing the low cost of fertilizers, whereas we see this bright pink and bright purple in Africa detailing the cost of ammonia is nearly 2, 3, or 4 times as high. So another challenge, as I alluded to earlier, is while we've been able to get economies of scale, that comes as a detriment to innovation and discovery. Today, in the United States, there's only 8 companies that have enough revenue to even finance building a Haber-Bosch plant. If you extrapolate that further to the continent of Africa, there's only 8 countries that have a GDP large enough to finance such an effort. Many of these countries, even if they have the finances, would not spend the money because it would be a significant portion of their GDP. a Haberbosch plant that costs $2 to $4 billion is not economical for most places, and therefore there has been a lack of innovation in this commercial space. The last thing I want to highlight is something that's happening right now, today. The variability in the cost of fertilizer is really outstanding. If you were reliant on creating a budget when you have a variable cost that varies by 2 to 3 times over the span of a year, it would make making profits as a farmer very challenging. You can see here, this is the cost of fertilizer throughout a year. You can see 2019, the cost, the 2020, the cost, but 2021 is tremendous, and even in the last couple of months, this has not been predicted, the cost. It is heavily tied to natural gas and inflation, and therefore farmers, even today in the United States, are foregoing buying fertilizers because of this exponential growth in the cost of fertilizers. So we find ourselves at an interesting point. Population growth continues to be a challenge, and it's been estimated that the production of food over the next 40 years will need to equal the amount of production over the last 8,000. We also are seeing this growth in really distributed places. Much of the population growth is occurring in areas which don't have access to fertilizers and don't use fertilizers. An example of that is in Africa, where 17% of the global population exists, and that percent is going to increase, but the fertilizer usage is less than 1% of the global fertilizer usage. And it's because it's too expensive. So we really need a shift in the paradigm of how we manufacture, distribute, and use fertilizers. And my group really advocates from moving away from a reliance on fossil fuels, the use of these solid fertilizers solely for supply chain and shipping reasons, and away from this centralized production in rich areas. We know that the solid fertilizers are not the most efficient, and so there's lots of reasons to move away from them. We advocate for a shift towards technologies that can enable the use of earth-abundant feedstocks and renewable sources, to move towards these liquid phase fertilizers and move them closer to the production, to the agricultural sites, so that you can manufacture these fertilizers. It's been shown by agricultural scientists that these liquid fertilizers are more efficient and they are effective. What's interesting to me at this time is also that when everyone always asks me, how are you going to displace the Haber-Bosch process? It's been effective for 100 years. And my answer is it's effective, but there's been a lot of innovations in 100 years that we haven't even looked at. So there are ways to redesign this process and lots of opportunity. We can explore new catalytic pathways. We don't have to stick with the same dissociative reaction mechanism that the Haber-Bosch process uses. We can look at oxidative pathways. We can use new feedstocks. We don't have to just use nitrogen as our feedstock. We can look at waste streams. We can examine cost reduction through combining reactions and separations together in a process-intensified way. And finally, as I've alluded to throughout, we can look at making fertilizers that look different, feel different, and are more effective for agricultural purposes. So at Georgia Tech, my group is working on 2 different areas. We are looking at how to design photocatalysts that can use sunlight to generate those photogenerated electrons and holes, and they can react with nitrogen and selectively adsorb nitrogen over oxygen, allowing for reactive separations and conversion of that nitrogen to ammonia. We are also looking at how you can take nitrogen compounds found abundantly in our environment, nitrate, and how you can convert nitrate to ammonia. I'll note that we have discovered 2 catalytic pathways which are different than the Haber-Bosch process. One that relies on interaction with carbon and one which uses nitrate, and they allow us to get to ammonia. Both catalytic reaction mechanisms actually are bio-inspired. We found that a lot of minerals in soils perform these reactions, and we're trying to augment that for our photocatalysts. And we know bacteria perform biological denitrification every day. And so we can control these reactions and use bio-inspired pathways to develop new ways to make ammonia. So the statement of 2 inventions that we are looking at in my group is, in terms of the photocatalyst, we're looking at a system which leverages a novel reaction between carbon and nitrogen to produce aqua ammonia. This is a liquid-based fertilizer that contains 10 weight% nitrogen. Our reactor uses low-cost air separations, adsorbents, which allows for the selective adsorption of nitrogen over oxygen, and so we can passively feed nitrogen into the reactor architecture. Nitrogen can then interact with our photocatalyst, with our carbon source, and we can convert nitrogen to ammonia. Right now, our carbon source is an organic matter that is abundant in these agricultural sites, but we're also looking at how we could use carbon dioxide as our carbon source to allow for simultaneous sequestration of CO2 and ammonia production. In our nitrate system, we are looking at an electrocatalytic system, which is a novel bimetallic catalyst, which allows for the selective adsorption of nitrate to one part of the catalyst and the catalysis of nitrate to nitrate. And then the nitrate, we're able to catalyze the selective conversion to ammonia on another part of our active catalyst. And so with that, I just want to summarize. My main goal is to talk to you about how we can harness the sun to decarbonize and distribute fertilizer production. If you asked me 5 years ago when I started in this area whether my technologies would be getting into the marketplace soon, I would have been honest with you and said, I do think this is a long-term goal, and displacing the Haber-Bosch process may be too ambitious. But if you ask me today, we've made a lot of progress and much faster than I imagined, and I believe that these technologies are going to be implemented in the near term. I'm excited to say that my students are beginning to take the work out of the lab and move to the demonstration scale to start to move this towards an actual technology that we can use, because simply put, the Haber-Bosch process is not sustainable, and it's been a little too long, and we need some more innovation in this space. And with that, I'm happy to answer any questions.
Hi, Marta, I'm back. Before we, get any questions from the floor, because I'm having here my iPad. If anybody wants to post something, I'm ready to go. But I have prepared something, because how does the fertilizer industry react when you basically come up with this sort of new idea and telling them, well, we could do it differently? Do they react like, okay, that's a great idea, let's get on board? Or are they going like, well, we've been doing this for so many years, why should we change?
Yeah, I would say that we work in a lot of different spaces, and I don't think that the chemical manufacturers are at all concerned about their process being displaced. When you look at other areas like electrofuels, they are more willing to adapt, but definitely the ammonia industry is not seeing that they need to adapt at all yet.
Okay. So is there a push maybe necessary, like the political framework, governments that need to come in and really nudge them in the right direction?
Yeah, I think that we're seeing the biggest policy changes in terms of increasing the amount of decarbonized electricity will enable a lot of new technologies in electrofuels broadly, and I think that policy change will aid in the electrification of fertilizer production, and so it may be a byproduct that we start with electrification of our grid, and that enables progress to be made on these fronts quicker.
And you showed on your map that basically Africa has a lot of food production going on, but not really a lot of fertilizer production. How can we make that change? Because you actually present them with a solution. Are there any initiatives already being made that maybe funding or some kind of NGOs that are already getting people excited about your solution?
Yeah, so if I'm discussing this with experts in the field, one challenge that they've highlighted is, there is a real need to be able to produce the fertilizers on site. Even just shipping free fertilizer or cheaper fertilizer doesn't because of the long distribution and the challenge in distributions, doesn't actually reach the farmer. So I think you need to actually have farmers involved in this process to enable it to grow. And if they can see success and if they can see profits as a result, I think that would be the biggest biggest thing that would drive its implementation.
We have some questions from the floor, so I would love to take those. The first one is, how does this new type of synthetic fertilizer compare with organic fertilizer? Which is better, all things being equal?
So in terms of, I think the key with a lot of times with some of the organic fertilizers is there's a variability associated with it from depending on who's making it. And so that's one thing that when talking with farmers, there has to be a very consistency about it. And so the difference with this is that it's still, you can have a high purity, highly consistent product that would be the farmers would be grateful for. So I think that would be one of the major differences. But I also think there's going to be different amounts of a place for organic fertilizers as well as just this aqua ammonia.
And there's another one that I would love to take. What is the projection of cost reduction brought by this process?
So we've been preliminary going through the techno-economics of this, and the main challenge, the main economic benefit that we're seeing is actually just the ability to do this in a scalable way. And so the Hagberg process is just, if you scaled it down to smaller regional places, it doubles, triples, it quadruples. And our cost really remains fixed at all scales. And so we think that is one of the major benefits in terms of the economics of it. But there's still quite a bit of economics that need to go in, and that's without actually any subsidies or any policy taken into consideration.
So we have a lot of questions coming. I'm happy that everybody's using the app now. Great. I'm not sure if we can get through all of them, so check in with Marta later on to contact her at the app. But I have maybe one more question that we can answer. What are your thoughts on companies like Pivo Bio, engineered nitrogen fixating microbes?
Yes, I'm very, I think it's fantastic. From what I've read, that's the direction we need to be going. We need to be going in a direction that we need to minimally apply fertilizers, and I think that approach has already shown to be effective in that it has reduced the need for application of synthetic fertilizers. I don't think, when talking to people in that space, they agree that they don't think that they're ever going to get to zero fertilizer, but I think that also would help our case, actually.
Thank you so much, Marta. You had a lot of questions, so I think people will get in touch via the app or otherwise, to contact you on LinkedIn or wherever. Thank you so much for your speech. Thank you.